Can a problem be undecidable for a computer? That's a big question. It sounds a bit like science fiction. Like maybe there are some mysteries out there a computer just can't crack, no matter how fast it is or how much memory it has. And the truth is, yes, that's exactly right. There are problems a computer simply cannot solve, ever. This isn't about how hard a problem is. We all know computers can struggle with really tough problems. Think about predicting the weather perfectly a month out, or designing a new drug from scratch. Those are incredibly complex. They need huge amounts of calculation. They might even be too complex for today's computers or even tomorrow's. But we usually think that given enough time, enough processing power, and enough data, a computer could eventually figure it out. Or at least get really, really close. But what we're talking about here is different. An undecidable problem isn't just hard. It's impossible. It's a problem for which no computer program, no matter how clever, no matter how fast, can ever give you a correct answer for all possible inputs. It's a fundamental wall, a limit built into the very nature of computation itself. To really get this, we need to think about what a computer does. At its core, a computer is a machine that follows instructions. It takes some information in, it crunches that information according to a set of rules, and then it gives some information out. So we call those sets of rules algorithms. Think of an algorithm like a recipe. A cooking recipe tells you step by step how to make a dish. It says, take 2 eggs, beat them, add a cup of flour, stir. And if you follow those steps precisely, you get a cake or whatever it is you're making. A computer algorithm is just like that. It's a precise list of steps. Read this number, add it to that number. If the result is bigger than 10, do this. Otherwise, do that. For a computer to solve a problem, it needs an algorithm. This algorithm has to meet a few conditions. First, it has to be clear. Every step must be unambiguous. The computer can't scratch its head and wonder what you meant. Second, it has to be effective. Every step must be something the computer can actually do. And third, and this is crucial, it has to stop. An algorithm has to finish its work and give you an answer. If it just runs forever, you never get a solution. You just get a machine humming endlessly. For many years, especially when computers were first being dreamed up, people had a lot of optimism. It seemed like, with this powerful new tool, we could solve anything. Just write the right set of instructions, and the machine would do the work. The sky was the limit. But then, a brilliant thinker named Alan Turing came along. He was working in the 1930s, long before most people even knew what a computer was. He wasn't just thinking about building computers, he was thinking about computation itself. He wanted to understand what it meant to compute something. What were the basic rules? What were the limits? Turing imagined a very simple theoretical machine. We call it a Turing machine. It's just a tape that goes on forever in both directions, divided into squares. Each square can hold a symbol. And there's a head that can read a symbol, write a symbol, and move left or right along the tape. The machine also has a set of states, like different modes it can be in, and a set of rules that say if you're in this state and you read this symbol, then write that symbol, move this way, and go into that new state. This sounds incredibly basic, doesn't it? Like a toy. But Turing proved something amazing. He showed that this simple machine could do anything any real computer could do. Any problem that can be solved by an algorithm on a modern supercomputer can, in theory, also be solved by a Turing machine. It might take vastly longer, but it's possible. This means if a problem is impossible for a Turing machine, it's impossible for any computer. This simple model became the standard for defining what computable actually means. And then Turing used his own machine to show something truly mind-bending. He showed that there are problems that are undecidable. The most famous of these is called the halting problem. The halting problem goes like this. Imagine you're a computer programmer. It would be really useful if you had a special program. Let's call it. What H does is take any other program, let's call it P, and any input for that program, let's call it I, and then H would tell you for sure if P will eventually stop running when given I, or if P will run forever in an infinite loop. Think about how useful that would be. You write a program, you feed it into H, and H tells you, yep, this program will eventually give you an answer. Or nope, this program will just spin its wheels forever. No more waiting around hoping your code finishes. No more programs crashing because they got stuck. It sounds like the ultimate debugging tool, doesn't it? It seems like something we should be able to build. After all, we can trace programs, we can look for loops, we can set timers, but Turing proved that no such program H can ever exist. It's impossible. How did he prove it? This is where it gets a little tricky, but the core idea is beautiful in its simplicity. It's a proof by contradiction. Let's pretend, just for a moment, that this magical program H does exist. So we're assuming it does, and we're going to see if that leads us to a logical dead end. If it does, then our initial assumption that H exists must be wrong. So we have our hypothetical program H. It takes a program P and an input I, and it tells us either P halts on I or P loops on I. Now, we're going to build a brand new, very special program. Let's call it PNU. Here's how PNU works. PNU takes another program, let's call it % as its input. Just one input, not a program and a separate input, just a program. Number 2, inside PNU, it uses our magical program H. It asks H this question: will program X halt if I give X itself as input? If H says yes, X halts when given X as input, then PNU goes into an infinite loop. It just runs forever. If H says no, X loops forever when given X as input, then PNU stops immediately. It halts. So PNU is designed to do the opposite of what H predicts for its input program X when X is run on itself. Got it so far? PNU is a program that uses H to check another program X when run on X itself, and then PNU does the opposite of H's prediction. Now for the kicker. What happens if we give PNU itself as input? What if we run PNU? Let's trace it using our hypothetical program H. Case 1 that you have as a kid, because as a kid, you're looking, if PNU halts, then according to the design of PNU, H must have told PNU that PNU loops forever when given PNU as input. But if H said PNU loops forever, then PNU's rule says it should have halted. So if PNU halts, it should have looped forever. This is a contradiction. Case 2, imagine PNU loops forever. If PNU loops forever, then according to the design of PNU, H must have told PNU that PNU halts when given PNU as input. But if H said PNU halts, then PNU's rule says it should have gone into an infinite loop. So if PNU loops forever, it should have halted. This is also a contradiction. In both cases, we end up with a contradiction. Our initial assumption that a program H could exist led us to a logical impossibility. This means our assumption was wrong. Therefore, no such program H can exist. The halting problem is undecidable. This is a profound discovery. It means there is no general algorithm, no master program that can look at any other program and reliably tell you if it will ever finish. It's not that we haven't found it yet. It's not that our computers aren't fast enough. It's logically impossible. It's like asking for a number that is both even and odd. It just doesn't exist. What does this mean in the real world? It means you can't build a perfect antivirus program that can scan any piece of code and definitively say, this code is guaranteed not to get stuck in an infinite loop and crash your system. You can build programs that try to detect loops, and they catch many of them. But there will always be some programs, cleverly designed, that will slip past any finite detection method. Or rather, any detection method that itself is guaranteed to halt. It also means that you can't build a perfect compiler or a perfect debugging tool that can automatically guarantee that your programs will always finish. We rely on testing, on careful design, and on human insight to try and catch these things. But we can't fully automate the proof of termination for all programs, and the halting problem isn't alone. Once Turing opened this door, other undecidable problems started to show up. Many of them are connected to the halting problem, meaning if you could solve one, you could solve the halting problem, which we know is impossible. One example is the post-correspondence problem PCP. Imagine you have a set of dominoes. Each domino has a word on its top half and a word on its bottom half. You want to line up a sequence of these dominoes, reusing them as many times as you like, so that the string of words on the top halves matches the string of words on the bottom halves. The question is, for a given set of dominoes, is it possible to find such a sequence? It sounds like a fun puzzle, a kind of word game, but it turns out this problem is undecidable. There's no algorithm that can always tell you if a solution exists for any given set of dominoes. Another famous one is related to mathematics. It's called Hilbert's 10th problem. David Hilbert was a very influential mathematician who, in 1900, posed a list of 23 unsolved problems that he thought would shape the future of mathematics. His 10th problem asked if there was a general algorithm that could tell whether a Diophantine equation has integer solutions. A Diophantine equation is basically a polynomial equation where you're only looking for whole number answers like times raised to the power of 2 plus y raised to the power of 2 as z raised to the power of 2, which has solutions like 3, 4, 5. For a long time, mathematicians worked on this. It wasn't until 1970 that a young Russian mathematician named Yuri Matyasevich, building on earlier work, proved that Hilbert's 10th problem is also undecidable. No general algorithm can solve it. What these examples tell us is that undecidability isn't just an abstract idea stuck in Turing's theoretical machine. It pops up in different areas, often in ways we wouldn't expect. It's a fundamental property of certain kinds of questions. It's important to understand the difference between a problem being hard and a problem being unsittable. A hard problem is one where there is an algorithm, but that algorithm might take an incredibly long time to run, or need an enormous amount of memory. Think of things like playing a perfect game of chess. We have algorithms for chess. They involve searching through possible moves, but the number of possible moves and counter moves is so astronomically large that even the most powerful computers can't explore every single path to find the absolutely perfect move for every situation. They can only search so far ahead. So chess is hard, but it's defeatable. In theory, if you had infinite time and memory, you could find the perfect move. We just don't have that. Another example is the traveling salesperson problem. Imagine a salesperson who needs to visit a list of cities and wants to find the shortest possible route that visits each city exactly once and returns to the starting city. There's an algorithm for this. You can list every single possible route, calculate its length, and pick the shortest one. But if you have, say, 50 cities, the number of possible routes is so huge that even the fastest computers can't check them all in a human lifetime. This kind of problem is called NP-hard. It's immensely difficult, but it's still decidable. We can always find the optimal solution given enough time. For practical purposes, we often use heuristics, clever shortcuts, that find a good enough solution quickly, even if it's not absolutely the best one. But an undecidable problem is in a different league. It's not about how long it takes. It's about the very idea that no algorithm exists at all. No matter how clever you are, no matter how much computing power you throw at it, you will never find a program that correctly solves it for all possible inputs. It's a mathematical wall. Why can't computers figure these out? It often comes down to issues of self-reference and infinite possibilities, much like the paradox we saw with the halting problem. These computers are fundamentally deterministic. They follow rules. When you create a logical loop or a situation where the answer depends on an answer that depends on itself in a circular way, the systematic, step-by-step nature of computation breaks down. The implications of undecidability reach across computer science and even into mathematics and philosophy. For software engineering, it's a sobering truth. We can't build perfect software. We can write tools that help us find bugs, that check for common errors, or that verify certain properties of our code. But we can never create a fully automated system that guarantees any arbitrary program is entirely bug-free or that it will always finish executing. This means humans are always going to be essential in software development for creativity, for understanding context, and for making judgment calls that algorithms can't. For artificial intelligence, it sets some boundaries. If an AI is built on algorithms, then it too will face these same fundamental limits. A general AI might be incredibly powerful and solve problems we can't even dream of, but it will still be constrained by the inherent undecidability of certain problems. It won't be able to solve the halting problem, for instance, any more than a human can write a program to do so. This tells us something profound about the nature of intelligence itself and what it means to solve a problem. It suggests that even the most advanced AI will need to deal with uncertainty and make pragmatic choices, just like humans do, rather than always finding a definitive algorithmic answer. In mathematics, the discovery of undecidability alongside Kurt-Gödel's incompleteness theorems, which showed that in any sufficiently complex formal system, there will always be true statements that cannot be proven within that system, fundamentally changed how mathematicians thought about what's provable and what's computable. It showed that there are inherent limits to formal logic and computation. It also raises philosophical questions. If computers, which are based on logic, cannot solve these problems, what about humans? Do we have some non-algorithmic way of solving things, or do we just get lucky and avoid the undecidable cases? The truth is, humans understand the proof that the halting problem is undecidable, but we still can't solve the problem itself for every arbitrary program. We might be able to figure out if specific programs halt using our intuition and experience, but not generally. Our understanding of the impossibility is what's unique, not our ability to magically bypass it. So, How do we live with these undecodable problems? We don't just throw our hands up in despair. We adapt. We use heuristics. For problems that are undecidable or even just incredibly hard, we develop rules of thumb that work most of the time. For example, antivirus programs don't try to solve the halting problem for every piece of code. Instead, they look for patterns of known malicious code, or they monitor programs for suspicious behavior. They make an educated guess, and they're usually pretty good, but they can never be 100% perfect. We bound the problem. Sometimes, we can take an undecodable problem and make it decidable by adding constraints. For example, the halting problem asks if a program halts eventually. That eventually is the tricky part. But if you ask, will this program halt within 10 seconds? That's a decidable problem. You just run it for 10 seconds. If it's still going, you say no. It's not the original problem, but it's a useful variation. We rely on human interaction. For complex software verification, we don't just run an automated checker and expect it to give a perfect answer. We use formal methods where skilled humans write mathematical proofs about their software, often aided by proof assistant software. But the ultimate responsibility and insights still lie with the human. The discovery of undecidable problems is a humbling one. It tells us that computers, for all their power, are not magic. They are powerful tools that operate within the strict boundaries of logic and algorithms. These limits are not flaws in our current technology. They are fundamental truths about what can and cannot be computed. Understanding undecidability helps us to be more realistic about what we can expect from computers. It helps us avoid wasting time trying to build systems that are logically impossible. Instead, it pushes us to be more creative. It forces us to think about how we can work with these limits using human intelligence and ingenuity to complement the algorithmic power of machines. In the end, the fact that some problems are undecidable isn't a failure of computers. It's a profound insight into the very nature of logic and information. It defines the edges of what we can automate and reminds us that some mysteries will always remain, pushing us to think deeper about the world around us. It's a fundamental part of the computational landscape, and it shapes everything we do with our digital tools.